Example 17. What is the strength and direction of electric field 1.0 meters to the left of a 3 microcoulomb charge? How does this change if the charge is negative instead? All right, so example 17. I've written down the pertinent information. Okay. So 3 microcoulombs radius is 1.0 meters. I want to find the electric field, right? Right? So we have to think, which equation do we need? There's two equation options here. We have E equals KQ over R squared, and we have E equals F over Q. So which equation should we use? KQ over R squared, right? We should use KQ over R squared because they're asking for the electric field created. The electric field created by the charge. Okay? So then I can plug in what I know. We know K is always 9 times 10 to the 9. So 3 microcoulomb charge. Which way is the electric field point surrounding a 3 microcoulomb charge? Out, right? The electric field lines will always point away from that one. So when I figure out the electric field, it's going to be pointing away from the charge. Oops. K is 9 times 10 to the 9 times 3 times 10 to the negative 6 because microcoulombs all over 1 squared. Right? So what does that mean? What does that make? Yeah, what? 27,000? Oh, I was right. Nice job. You are right, Derek. 27,000 newtons per. Does that make sense? And it points out. Okay? I think they said to the right, didn't they? Right? They said 1 meter to the right. Did they say in the problem? Okay. Oh, 1 meter to the left. Sorry. So if I'm on the left of this 3 microcoulomb charge, which way is the field point? To the left. Now, how will this change if we had a 3 microcoulomb charge, but it's a negative charge now? Instead of being an absence of electrons, we have too many electrons. All right. What happens here? Good. The field lines all go in. Okay. So instead of having this be an electric field that points to the left, it'll now point to the right. So if this were to change to a negative charge, the electric field on this side would point towards the charge. Because when this is a negative charge, that 3 becomes negative, making the 27,000 negative, and negative means in. Does that make sense, guys? Does that make sense?
Yes.
Yeah. Gentlemen, we're not comparing cell phones right now. All right. Example 18. Small test charge is placed 0.04 meters to the right of an electron. What is the magnitude and direction of the electric field at this location? So we're to the right now. All right. So I tried to draw a picture here for 18. All right. Same situation. We have the same two equations. Which equation should I pick? Which equation should I pick?
The first one.
Okay, we want to know the electric field created by the charge, right?
Same one that we used.
Yep. So the same one we used previously. Okay. So we want to know the electric field. Oops, that's not. We want to know the electric field right there. Okay. We don't know the electric field. So it's the same equation. Now it's an electron. Which way is it going to point? In or out? Point in. And I'll show you why. So electric field is going to be equal to KQQ over R, or KQ over R squared, sorry. So electric field is going to be 9 times 10 to the 9th. Now the charge creating the field is an electron, right? Right? What's the charge on an electron?
Negative.
Negative 1.6 times 10 to the negative 19 all over our radius, which was 0.04 squared. Now, since the charge is negative, what's going to happen when we calculate this? We'll get what? We'll get a negative number. We'll get a negative number. So 9e9 times negative 1.6e negative 19 divided by 0.04 squared. What do you get?
Negative 9 times 10 to the negative 7.
Good. So negative 9 times 10 to the negative 7 newtons per coulomb. And since it's negative, that means it points inward. Are there any questions about that? No questions?